Hey everyone, welcome back to the last reinforced learning introduction tutorial series. I will say that first, this tutorial will be about proximal policy optimization implementation, but as always, first I begin with short theory introduction and then we'll go to the code part. So I'll try to cover this quite fast, but because it will be quite short implementation, you'll see everything. Actually, in 2018, OpenAI made a breakthrough in deep reinforcement learning. This breakthrough was made possible thanks to a strong hardware architecture and by using the state-of-the-art algorithm proximal policy optimization. The main idea is that proximal policy optimization avoids having too large policy update. To do that, it uses a ratio that tells us the difference between our new and old policy and clip this ratio. Doing that will ensure that policy bit will not be too large. In this tutorial, I will dive on the understanding of the proximal policy optimization architecture, and we will implement this PPO agent that learns to play PONG v0. However, if you want to understand this tutorial called Proximal Policy Optimization algorithm, you need first to check all my previous tutorials, and mainly as a backbone I will use asynchronous actor critic tutorial code which I made in the previous tutorial. So if you were reading my tutorials about proximal policy gradient, I talked about policy loss function. The idea of this function was we were doing gradient ascent step, which is equivalent of taking reversed gradient descent. This way our agent is pushed take actions that lead to higher rewards and avoid bad actions. However, the problem comes from the step size. In the training process might give you too slow learning, and too high step size might give you a much bigger variable in the training. That's where proximal policy optimization is useful, and the idea is that PPO improves the stability of the actor training by limiting the policy update at each training step. To be able to do that, Proximal Policy introduced a new objective function called clipped surrogate objective function that will constrain the policy change in a small range using a clip. So I will show you an image here about clipping. First, as explained in PPO paper, instead of using log p to trace the impact of the action, PPO used the ratio between the probability of action under current policy divided by the probability of the action under previous policy. However, if the action taken more probably in our current policy than in our former, this will lead to a larger policy gradient step and consequently an excessive policy update. So with clipped surrogate objective function, we have two probability ratios, one non-clipped and one clipped in range, and one of them is 0. If we take the minimum of the clipped and non-clipped objective, the final objective would be a lower bound of the clipped objective. And consequently, we have two cases to consider when the advantage in our function is more than 0 and advantage is negative. So if advantage is more than 0, it means that the action is better than the average of all the actions in the state. Therefore, we should encourage our new policy to increase the probability of taking that action at that specific state. However, because of the clip, it means that action can't be 100 times probable compared to old policy because of the clip. This is done because we don't want to update our policy too much. Taking the action at specific state is only one try. It doesn't mean that it will always lead to a super positive reward. So we don't want to be much greedy because it also can lead to the bad policy. So this shortly about positive advantage, and when advantage is negative, the action should be discouraged because negative effect of the outcome. Also, we don't want to make a big change in the policy by being too greedy by completely reducing the probability of taking that action, because it leads to negative advantage. In summary, thanks to this clipped surrogate objective function, the range that the new policy can vary from the old one is restricted, because the incentive for the probability ratio to move outside of the interval is removed. So if the ratio is more than 1 plus e or lower than 1 minus e, the gradient will be equal to 0. It means there won't be any slope. So both of these clipping regions prevent us from getting too greedy and trying to update too much at once, and updating outside of the region where this sample offers a good approximation. I think it's kinda hard to understand everything from theory, but it's better would be if you might read the theory on my website, or you probably should read original paper, then you might understand everything more in details. But actually they are not doing any hard stuff that it could be not understandable. See, in simple terms, they are not allowing too greedy steps in negative or positive way. Now I'll go to the code and simply will try to implement it. Same as before, I will use my asynchronous actor critic agent. This means that I will use my previous tutorial code as a backbone, and there will be the same process explained as in my previous tutorial. So same as before, I will bold code which is new, and all code be stroked through in my text version tutorial. Then you might easier can track changes in code. So from your side, it looks that it's really difficult to implement proximal policy optimization, but in practical, we already have prepared code to be simply adapted to use proximal policy optimization loss function. So we will need mainly to change our loss function, and we need to change our model, and we'll need to change our replay function. So actually, before we were using a categorical cross entropy function, right now we'll use a PPO loss function. This will be a custom loss function which I will create right now. So after dense actually, I will define a new PPO loss which will have I true and I predict values. And I'm not going into details here because I will cover this more in my text version tutorial, because when talking it's much harder to understand than reading the code. So at first we will take all the values we give to our training agent. So I will write advantages we'll use. This will use some kind of prediction picks and actions, and we'll take this from iTrue function. Actually, it will be easier if I will come to this function later. So I will now change more code in my replay function than in my model. So I will come back to model because this way will be easier to understand everything. So I go to my act function. Here we need to return a prediction, our choice. Then we go to our replay model. Here we need to change, also we need to prediction 0. And here we also need to convert these predictions to NumPy array. And now I will use discounted reward in different way. So I will need to stack them. NumPy stack simply. This way I'm not going to use this anymore. So our discounted rewards and values will be the same shape. And I am going to calculate my iTrue value. And I do this by calling a NumPy height stack function. Actually, you may ask what is the NumPy height stack used for, because I use a custom loss function. We must send data in the right shape of data. So we pack all advantages, predictions, actions to iTrue, and when they are received in custom loss function, we pack it. I'm writing it like that I have here advantages, predictions, and actions. Actually, to understand it better, you might print a shape of this value, so you will understand it better. And next, I will change actor fit. So here I'm not feeding actions. Here I'm using iTrue function. iTrue, and here I can write epochs, and here I will create a new parameter, epochs, because in this way we can use more epochs if we have our computing resources. And of course we need to add a shuffle. We are shuffling our training data. This means that we'll train it shuffle priority, and then I just give a length. Our batch size is length of rewards. Actually, we do the same with our critic network. Shuffle true, batch size, epoch, sub epoch. Okay, and now I will return to the beginning, and I will just write self epoch equal to 10, or well, actually it will eat a lot of resources for my GPU, but actually it's not a problem for me. And now when I've finished this function, we have this following value in here in actor, and now we need simply to unpack these values and to get them the same as they were sent here, to unpack them in a loss function. And mainly we use hstack function because we can simply send values as a list to our agent to fit. So actually, let's go back to our model. Now you might maybe understand why I'm doing this. And where is my loss function? Yeah, so here will be iTrue, and first value sent will be everything till the 1. Then I'm picking the iTrue again, and here will be from 1 till the 1 plus action space, and one more will be equal to iTrue, and will be that, and everything after that. Now, in a paper you might see that they are using loss clipping, so I'm writing it following way, and they use entropy loss. You might try to play with these constants, but it's up to you. And now we just calculate our loss function as they do in the paper. So we do everything Keras way. So I write I predict will be multiplied by actions, and we then calculate an all probability, which equal to actions multiplied by prediction space. Then we calculate our ratio, and calling it just our ratio, which will be calculated by probability divided by old probability, and we need to add some kind of constant. And then we calculate value of P1, which are equal to ratio multiplied by advantages, and then we calculate another value, which is kind of hard to implement, and I'm not sure if I will write it correct, but we'll see. And there will be use a clip between minimum value of 1 minus loss clipping and max between max value equal to 1 plus loss clipping. This is actually what I was talking from that image I showed you before. Call it surrogate function. And at last, we need to calculate a loss function, which is the mean of k dot minimum of in P1 and P2. And to this we add an entropy loss multiplied by minus prob multiplied by a dot log, and this prob with some kind of constant. And actually we wrote our loss function, and simply now we need to return it. Return loss. When I'll try to build model, we'll see I made mistakes or not, it doesn't matter. And you better copy the code from my GitHub tutorial or web tutorial, because I will check if I wrote this loss function correctly. Because everyone is human and everyone might make some kind of mistakes. So I can do. So actually we wrote a custom loss function. I made it different in predict function. Now we need to do some changes in run function actually. And here we had a reward. I need to add predictions that are equal to nothing, and after action we need here to take this prediction, and this prediction be appended predictions append prediction, and that's it. I made these small changes in here, so I need to make these small changes in my threading function also. I'm trying to just copy the code from here. Actually should be the same. We don't have, we have a memory. Actions, predictions. Yeah, it seems the same for me. And yeah, here we don't need a cell, and here we don't need a cell. This would be a mistake from my side. We simply added same lines to define a threading function, and that's all. We have just created an engine that can learn to play an Atari game. So first, let me try to run it in asynchronous way. So this is simply would be a PPO, and this would be a PPO. I will change these names later, or I already changed this in the beginning. I don't know. Let's check. No, I didn't change. So anyway, I will change these later. Let's now try to build this in simple PPO way. Here, right on deterministic. Yeah, it's something with tabs. Okay, line indentation and burn indentions tabs. Everything should be fine now. Let's try to build this again. Missing wonder card. Yeah, forgot this totally. Self replay, and we had add here a predictions at the end, and I go to the threading. I'll do the same here. Predictions. Build this again. So here comes the errors. Let's see. Okay, I'll try this on CPU. Let's see if I'll receive same error. Yeah, we don't need this, I think. Let's try this now. Yeah, everything is fine here. So I will cancel build, cancel build. And at first I will change this to 1000 steps, apples 10, and of course I will use a GPU. And that's it. Let's run this with some kind of threads, like 5 threads, okay? And keep in mind that sometimes I receive some kind of strange error with threads and it doesn't start training, so I couldn't find out what is the problem. But let's see if I'll receive it right now. Act is not defined. Fiction. Okay. Cancel build. Fiction. Yeah, by mistake I removed this. I try it again. Yeah, you might see this is the error I receive usually, and I don't know what's the problem. I will just need to rerun this. Oh, sorry. Where is my... I pressed escape by mistake. So, see, training. Yeah, as you can see, I didn't receive any errors right now, and actually, I think it's working. Our proximal policy optimization algorithm is training right now on this simple deterministic environment, and same as before, I'm not sure if I will train it for 500 steps, if I will see that agent is training much faster. For example, if it will reach maximum scores near 600 or 500, I will kill it and simply I will show you the results. But right now, results will be later. So now, the same way as before, I will stop the recording and I'll keep training. I don't know what I will do, but also I think I will do training for this PONG game, and we'll see later after I finish training. So see you later. So actually, here I am, and I'm back, and I finished training the agents as I said. I trained 3 different agents, and yeah, actually it took me a while, but I already did a lot of them. So at first, same as before, I trained PONG deterministic agent and PONG v0, same as before. From all my previous reinforcement learning tutorials results, these were the best. In PONG deterministic, we reached the best score in around 400 steps, while in asynchronous banded actor critic previous tutorial, we needed 800 steps. So here's the results. As you can see, actually, even after 300 steps, our results were quite satisfied. And I couldn't believe that this agent could be so good. And here are the results for my PONG v0 environment. Oh no, not PONG v0. This is one. This is one my PONG v0. As you can see, I never before with any other agent haven't seen this quite nice result. Actually, in 2000 steps, we scored about 10 scores of average, and after half time of training, actually it was averaging on 16 or 17 average score. It's actually it even trained this in much faster way. By the way, my goal wasn't to make it best, just to compare it with the same parameters, and I'm really satisfied with the results. And what I should say that I tried to train our convolutional neural networks. I uncommented these lines and I tried to train it. And actually training was twice as long as only with this dense layer. But yeah, I wanted to do this because actually model was much smaller than one dense layer. As you can see, it's 25 megabytes of size. This means that I will be able to upload this to GitHub. And if you don't have resources to train your own model, you can test my model. So actually, you can check how my model performs. So I will try first my simple model with dense layer, and then I will show you how my convolutional neural network model works. So let's run this, and here it is. This is our agent playing in the right direction, and as you can see, it's crushing the computer. Actually, computer is able to sometimes hit 2-1 score. Actually, I couldn't expect that nice results. And let's see how my convolutional neural network performed. Also, I didn't show you the graph, how to train it, but I was training it only for 10,000 of steps because it needed much more computational resources, and it was harder to train actually because I used a convolutional neural networks. As I could, as you can see, it was growing and growing, and probably if I would train it for 20,000 of steps, it would hit the same results as we had with our simple network. So let's see how my convolutional neural network performs. We saw right now how it was the simple dense layer, and actually it's also winning, but not that nice as before. But actually I'm winning here because right now my model is 4 times smaller than before, so I will be able to upload this to GitHub. Also, I wrote a small code modifications where I would be able to create GIFs from these uh, environments, and also I will upload both of them into GitHub, so you'll be able to use them. So that's it with my Proximal Policy Optimization introduction tutorial. Don't forget to implement each part of the code by yourself. It's really important to understand how everything works. Try to modify the hyperparameters. Use another gym environment. Experimenting is the best way to learn, so just have fun with this environment. I hope this tutorial could give you a good idea of the basics of proximal policy optimization algorithm. You can now move on to building upon this by executing multiple environments in parallel in order to collect more training samples and also solve more complicated game scenarios. For now, this is my last reinforcement learning tutorial. This was quite a long journey where I really learned a lot of, and I plan to come back to reinforcement learning later this year. This will be more practical and more interesting tutorials to come. So we'll see you in the next tutorials. So for now, thank you all for watching. I hope this was useful for you, and see you in our next tutorials. Goodbye.